Hi, welcome to Unit 7, Day 3. This is Part 1, Mole-to-Mole Stoichiometry Conversion, Conceptual Understanding. So as you know, in this unit, we're covering stoichiometry. And in stoichiometry, we use mole ratios to convert from the amount of one thing to the amount of something different. Now, in the previous lessons, we used the subscripts in chemical formulas as our mole ratios in problems like how many hydrogen atoms are there in 5 grams of water. So in this case, we are trying to convert from our mass of water to the number of hydrogen atoms. Notice that the substances are different because water is not the same thing as hydrogen atoms. And the amounts we're going from are from the mass of water to the number of hydrogen atoms. In this example problem, we would use the mole ratio from the chemical formula. We know from the chemical formula that if we have one water molecule, we would have 2 hydrogen atoms. So therefore, if we have one mole of water molecules, we would have 2 moles of hydrogen atoms. And this becomes our conversion factor. This mole ratio becomes a conversion factor we use to solve this problem. Now, in today's lesson, we are going to use the coefficients in the balanced chemical equation, not the subscripts, for our mole ratio. So in a problem like how many grams of H2, which is hydrogen gas, do you need to make 5 grams of water according to the reaction? 2H2 plus O2 goes to form 2H2O. So in this case, we're converting from mass of water to the mass of hydrogen gas. And if we go to the coefficients in the balanced chemical equation, we see that according to this equation, there's 2 moles of water and 2 moles of H2. So those become our mole ratios, the coefficients. Now, before we go into looking at problems, I just want to also go over, if you've not seen the video for extra help on stoichiometry, how we learn stoichiometry. Learning stoichiometry involves 2 types of knowledge. There's conceptual understanding, which has to do with reading comprehension and also understanding the science behind what you're learning in stoichiometry. But there's also problem-solving skills, which involve identifying and analyzing key information and the math that you use to solve the problem. Now, our brains typically process these types of information separately, so it's hard to learn them both at the same time, particularly when you learn something new. But it's important that you have both pieces of understanding for a complete understanding of stoichiometry. So what we're going to do is we're going to break this down. And in part 1, we're going to focus on the conceptual understanding, just so you get a sense of what these problems are actually asking you and how would they be relevant to a chemist. So a good way to understand the conceptual understanding is to compare a chemist to a chef. Now, many of us, even if we're not great cooks, we have cooked things before, whether it's a box cake mix or an elaborate meal, we have some understanding of how to deal with recipes when we're making something. So in the case of a chef will use a recipe to know how much of each ingredient to measure out and to determine how much food can be made from those ingredients. A chemist will use a balanced chemical equation to know how much of each reactant to measure out and determine how much products can be made. So there are a couple of key pieces of this analogy. For a chef, they use a recipe. A chemist uses a balanced chemical equation. So recipe and balanced chemical equation, they're giving you the same type of information. In terms of ingredients, and under a chemist's point of view, from a chemist's point of view, that would be the reactant. So ingredients and reactants are analogous, and the food that's made are like the products that a chemist would make. Now, keeping that in mind is important conceptually when you're tackling these problems to understand, like, what are they actually asking you? So before we get into some chemist scenarios, let's look at some chef scenarios. So let's say you have this recipe for chocolate chip cookies. And you want to know how many cookies you can make if you have 5 cups of flour. And just a quick note, you have enough of all the other ingredients to use up the 5 cups of flour. So none of the other ingredients are limiting. But how many cookies can you make from the 5 cups of flour? So if you would like, you can go ahead and pause the video now and give yourself a chance to think about that answer. Well, likely if you looked at the information here, you would probably say 40 cookies. And the reason why you would say 40 cookies, because what you would do is you would identify the ratio of flour to cookies, and you notice from the recipe highlighted there in that light orange, there's 1 cup of flour would make 8 cookies. Well, in this case, since you're using 5 cups of flour, you scaled up that ratio by a factor of 5. So since 1 cup of flour makes 8 cookies, 5 cups of flour would make 8 times 5, which is 40 cookies. Now, those parts of a chemical reaction, like the ingredients, which are like the reactants, which are like your ingredients, and the products, are important to keep in mind, because the same way you tackle that first scenario, you're going to tackle other scenarios that involve chemical reactions. Now, what about the measurements? In the recipe, the measurements are listed here as cups, teaspoons, etc. But in a chemical reaction, the measurements come from the coefficients in the balanced chemical equation. Remember, these are also known as molar coefficients. So we can read this reaction up here as 1 mole of lead nitrate plus 2 moles of potassium iodide make 1 mole of lead iodide and 2 moles of potassium nitrate. So our measurements here would be those coefficients in the balanced chemical equation. Okay, now let's take a look at some scenarios now that involve chemical reactions. So in this scenario, a chemist wants to make 1 mole of lead iodide. How many moles of potassium iodide does the chemist need? So to answer this question, we need to go to our recipe, our balanced chemical equation, and we see we're given lead iodide, and we're trying to find here potassium iodide. Now we know that according to this balanced chemical equation, we would make 1 mole of lead iodide from 2 moles of potassium iodide. So therefore, according to the coefficients of the balanced chemical equation, to make 1 mole of lead iodide, you're going to need 2 moles of potassium iodide. Now, what if instead of making just 1 mole, chemist wants to scale that reaction up to make 14 moles of lead iodide? How many moles of potassium iodide does the chemist need? And remember, potassium iodide is Ki and lead iodide is PbI2. So if you have 14 moles of PbI2, how many moles of Ki do you need? Well, again, we go to our balanced chemical equation, and we're given lead iodide once again, and we're trying to find potassium iodide. And we know from the coefficients that there is a 2-to-1 ratio, so 2 potassium iodide to 1 lead iodide. So to make 14 moles of potassium iodide, you would need twice as much, to make 14 moles of lead iodide, PbI2, you would need twice as much potassium iodide. So for 14 moles of lead iodide, you would need 28 moles of potassium iodide. Let's try this scenario. A chemist weighs out enough potassium iodide to have 5 moles of potassium iodide. The chemist needs at least how many moles of lead nitrate to react with the 5 moles of potassium iodide? So once again, we go to our balanced chemical equation and we look at the ratios from the coefficients. So according to the balanced chemical equation, there's a 2-to-1 ratio of Ki to PbNO3. So if I have 5 moles of Ki, how many moles of PbNO3 do I need? Well, you can see from this ratio that you need half as much lead nitrate, half as much PbNO3 as Ki. So if you have 5 moles of Ki, you would need half of 5 moles, which is 2.5 moles of PbNO3. All right, now I want you guys to try it with this CFU. So we have a new chemical reaction equation. And in this scenario, a chemist weighs out enough aluminum chloride to have 4 moles of aluminum chloride. So here's aluminum chloride. The chemist needs at least how many moles of barium hydroxide to react with the 4 moles of AlCl3? So go ahead and pause the video now, and when you press play again, the answer will be revealed. Okay, so the first thing you want to do is you want to go to your balanced chemical equation, look for your given and your find, and then we'll use the coefficients there for our ratios. So according to the balanced chemical equation, 2 moles of, it's a 2-to-3 ratio, so 2 moles of aluminum chloride to 3 moles of barium hydroxide. Now, since 2 moles of aluminum chloride needs at least 3 moles of barium hydroxide, 4 moles, so doubling that, would have to double this coefficient as well, right? So 4 moles of aluminum chloride would need at least 6 moles of barium hydroxide. So essentially what you did was you scaled up the reaction, you doubled the recipe. All right, try this CFU now. A chemist weighs out enough aluminum chloride to have 4 moles of aluminum chloride. So the same amount we start off with, 4 moles of AlCl3. If the chemist has at least 6 moles of barium hydroxide, so that part's good, can the chemist theoretically, how many moles of aluminum hydroxide can the chemist theoretically make from the 4 moles of AlCl3? There's a lot of information to tackle here, but essentially what they're saying is how many moles of aluminum hydroxide can you make with 4 moles of AlCl3? So pause the video now, and when you press play again, the answer will be revealed. So here's our process. We go to our balanced chemical equation. We see the ratio. The ratio here is a 2 to 2 mole ratio, or you can also say 1 to 1 mole ratio. So if you have 2 moles of aluminum hydroxide, you're going to make 2 moles of, aluminum chloride, you would make 2 moles of aluminum hydroxide. If you had 4 moles of aluminum chloride, you would therefore make 4 moles of aluminum hydroxide. You could just tell that from the coefficients. It tells you the ratios. How's our last CFU here? A chemist weighs out enough aluminum chloride to have 0.597 moles of aluminum chloride. The chemist needs at least how many moles of barium hydroxide to react with the 0.597 moles of aluminum chloride? This one's a bit tricky because in all the other problems, you pretty much can do mental math, scaling it up mentally in your head or scaling it down. In this case, it's not as easy because the numbers are a bit trickier, but I want you to give it a go, and then when you press play again, the answer will be revealed. Great. So as I said here, the mental math is more difficult in this problem. But once again, we would still go to the balanced chemical equation to see our ratios. It's a 2 to 3 mole ratio, so 2 moles of aluminum chloride needs 3 moles of barium hydroxide. Well, if we have 0.597 moles of aluminum chloride, how many moles of barium hydroxide do we need? Well, the answer for that is actually 0.896 moles of barium hydroxide. And essentially what you would do is you would multiply the 0.597 by 1.5. That's how you would get that number. But where does the 1.5 come from? How do you do this math and if you're not really quite so sure? Well, there's many ways to do it. But as you're going to see, we're going to use the same sort of math technique we've been using, which is dimensional analysis. But conceptually, the important part is that you can see that we use the ratios the same way you would use in a recipe. We use the ratios or the coefficients in the balanced chemical equation to tell us how much of each reactant that we need and how much of each product that we need relative to one another. All right, so in part 2, we're actually going to go into doing some more problem solving. So we can tackle problems more like CFU3 where the numbers are a bit tricky. You can't do it using mental math. All right, that's it for this video. Have a quality day.